Hello students, in the last lecture we studied classification basis on the mode of polymerization, and in that mode of polymerization we studied addition polymerization, after that condensation polymerization, and then ring opening polymerization. In this ring opening polymerization we had seen the example of the formation of nylon 6 from epsilon caprolactam. What is the epsilon? I explained last time. Epsilon is the fifth letter in Greek, and in our chemistry, when there is a functional group, to this functional group next carbon is alpha, then beta, then gamma, then delta, and then epsilon. To this epsilon, here it is the NH and then CO. So this is our epsilon caprolactam. So when we use catalyst as a strong acid or base, here it is a breaking of bond, and after that breaking of bond, that chain is open. This chain is open over here at these two ends, chain open, and then we get just like this one. After opening this chain, one monomer, here it is, and then they are connected to each other with these links, and there are formation of the n number of open caprolactam, epsilon caprolactam ring attached to each other, open one. So here it is, this the open end, this is the open end, here is the breaking of bond, and then we get this polymer, that is n number of monomers attached to each other, those are the polymers. Okay. So now next classification of the polymers is based on the basis of intermolecular forces, based on intermolecular forces. Now see, we know the intermolecular forces from when you started learning chemistry. From that year you know the intermolecular forces. Okay. Now related to these intermolecular forces, in our 12th standard polymer topic, there are four types. Those are the elastomers, then fibers, then thermoplastic, and then thermosetting. Thermoplastic and thermosetting. Now what are the elastomers? This is a very common thing. The most common word for this elastomer is rubber. This is our rubber. Okay. Rubber band. This is our rubber band. What is this? This is nothing but elastomer. Elasticity is a property by which substance gets stretched by external force. See, I am applying external force at this end, and I stretch this like this. I stretch this rubber band like this. I am applying external force and stretch this rubber band like this. Okay. And restores its original shape. This is this original shape. When I am going to apply external force, it is stretched in this way, and again this restore its original shape. This is original shape. Okay. So these elastomers, they are known as elastic polymers. They are known as elastic polymers. They are having very weak van der Waals type of intermolecular forces which permit the polymer to be stretched. Van der Waals forces are very weak in this, and that's why it permits polymer to stretch. A few crosslinks between the chain helps the stretched polymer to retract to its original position. There are some crosslinks are also there. Crosslinks we studied like this. Crosslinks are in between two straight polymers in this way, and this is the crosslink. Okay, this is the crosslink. These are the monomers which are linked to each other. These are the monomers which link to each other, and this is the cross link in between these two. Okay. So these cross links between the chains help the stretched polymer to retract to its original position. You must remember this word, cross links. Okay. For the MCQ also this word is very important, and when we remove that applied force, it retract to its original position. Now what are the examples? That is the vulcanized rubber, then Buna S, Buna N, and neoprene. Buna S, Buna and neoprene. Please remember all these examples. Examples under which category? Elastomers. So make a table of this and do the additions of all these types with all these examples. So one example is not particularly for that, that must have some different properties which we discussed before or after. So you have to mention those also. So you will have a clear cut idea about all these examples. Next one is fibers. Okay, fibers are nothing but polyamides. Polyamides. We studied such type of polyamides in our protein also, in biomolecules, proteins. So for example, nylon 66. If there is a polyester, then the commercial name is terylene. Commercial name is terylene. In these fibers also, the intermolecular forces is going to play a main role. Now what is this? See, these fibers, nothing but the polymeric solids which form threads, are called fibers. We know this very well. Threads are called fibers. These fibers possess high tensile strength, which is a property to have resistance to breaking under tension. Okay. This characteristic is due to the strong intermolecular forces like hydrogen bonding and strong dipole-dipole forces. We are so many times we studied this hydrogen bonding and dipole-dipole forces. Okay, the very important thing is that this is very strong intermolecular forces. And why this is so? Because in fibers we observe hydrogen bonding as well as strong dipole-dipole force. Due to these strong intermolecular forces, the fibers are crystalline in nature. These are crystalline in nature. And for example, polyamides, that is a nylon 66, and the polyester which we call as a terylene. See, this is nothing but a yarn, means this is nothing but a fiber. This is nothing but a fiber. Before this, in case of this ring opening polymerization, we studied nylon 6. This is also polyamide. See, NH is there, C double bond O, so that is the amide linkage, and the so many number of monomers attached to each other. So this is polyamide. Okay. Similarly, we are going to study in nylon 66 also. Nylon 66, where there are the two different monomers are going to attach to each other, and that's why we are going to count as a 6 and 6. Here it is 6, means this 5 and this is one more, so total are 6. That's why we represent this as a 6, nylon 6. Okay. Now next one is thermoplastic polymers. Thermoplastic polymers. Now these thermoplastic polymers are nothing but for polythene, which we use day to day life, those are the bags. Then polystyrene. Polystyrenes, CD and DVDs are made up of polystyrene. Okay. Then polyvinyls, we know the PVC pipes. PVC pipes, this is a very commonly used word, PVC. Those are nothing but the pipes. So polyvinyls, short form is the PVC, and from that we get pipes. Okay. What is this thermoplastic polymers? Plasticity is a property of being easily shaped or molded. Remember this thing, easily shaped or molded. Thermoplastic polymers are capable of repeated softening on heating and hardening on cooling. Please get this point, this is very important. Polymers are capable of repeated softening on heating and hardening on cooling. These polymers possess moderately strong intermolecular forces that are intermediate between elastomers and fibers. Okay, elastomers and fibers in between. These are the intermediate. We studied elastomers as well as we studied fibers, and in elastomers that is very weak, while in fibers the intermolecular forces are very strong and it is intermediate. For the thermoplastic, it is intermediate in between these two. And for example, as I told before, that is the polythene, polystyrene and polyvinyls. Okay, see, these are our plastic bottles generally we use for the mineral water and everything. That is nothing but we called it the PET bottles. PET. So what is the long form of PET? That is the polyethylene terephthalate. T stands for terephthalate. Polyethylene terephthalate, that is PET. Next is thermosetting polymers. Thermosetting polymers. And for example, there is a bakelite and urea formaldehyde resin. Bakelite we know is very well, that is the bad heat conductor which is used in transistors and everywhere, and urea formaldehyde resin is somewhat the connecting material which is made up of polymers. Okay, what is this? Thermosetting polymers are rigid polymers. Okay, these are the rigid polymers. During their formation they have property of being shaped on heating, but they get hardened while hot. Once they harden, they become infusible, means they cannot going to get, after cooling they will get shape of the different thing whatever we want. So they cannot be softened by heating and therefore cannot be remolded. This is very important, cannot be remolded. And this characteristic is the result of extensive cross linking by covalent bonds formed in the molds during hardening or setting process while it is hot. And such type of industrial brackets where there is a friction or something, but we should not have any effect, then at that time these industrial brackets are made up of this bakelite. Okay, this bakelite, and that is the important part of this thermosetting polymers. Okay, now next one is basis of different monomers, and there are two types. One is homopolymers, another one is copolymer. What do you mean by homopolymer? Means only one type of repeating unit, one type. Now polythene, we may call it as polyethene, or commonly we can say polythene. What is the repeating monomer here? That is the ethene, repeating monomer. If it is polypropene, then repeating monomer is propene. In nylon 6, repeating monomer is epsilon caprolactam. Are you getting this point? So this is homo, only one type of repeating unit. While in copolymer, more than one means two or more. More than one means two or more types of repeating units. So they are having two different monomers, they connecting to each other, and that is going to repeat one by one. And the example for this is the Buna S and Buna N. We will see this afterwards. Okay, here it is in copolymers. See which are the monomer and which are the polymer. This all things is given in this table. You please go through this problem 15.1 and try to understand which are the monomer polymers and which are the copolymers. Means which are the homopolymers. Homopolymers means only one type of repeating unit, while in copolymers two or more types of repeating unit. Here it is given very clearly. Okay, if it is ethylene monomer, then the polymer is the polyethylene, only one single unit, only one unit. Here it is, we can see there are the two units like hexamethylene diamine and adipic acid, but actually they connected to each other and form one monomer. Okay, though we can see there are, now we will see this example afterwards, only I am just giving you some simple idea about this. This is made up of hexamethylene diamine and adipic acid, but they already connected to each other, and these two going to add to each other and form one monomer, and that monomer, suppose this is one monomer, that is going to repeat like this, and that is going to connect to each other, that is going to connect to each other, such type of green bond, such type of bonds, it is connected to each other. So this is nothing but monomer. Okay, then here it is in bunais, it is copolymer, because this is totally butadiene and styrene and they randomly attached to each other. They are not connecting to each other in one step and then they are going to form a polymer, and that's why this is copolymer. More than one, two are there. Okay, so please go through this box, that is 15.1. So you will have a very good idea about homopolymer and copolymers. Now next is very important, okay, and this is based upon biodegradability. This is based upon biodegradability. Okay, we know by what is biodegradable. So first of all we will see non-biodegradable polymers. Okay, what is this? The synthetic polymers which are not affected by microbes, synthetic polymers which are not affected, this is important, not affected, not affected by microbes. Microbes are the organic compounds, okay, and this causes pollution hazards. This is very important, which causes pollution hazards are known as non-biodegradable polymers. But now what is biodegradable? These are natural fibers, means cotton, silk, wool, jute, all these are natural fibers, or few synthetic polymers also, just those are processed one, and we are going to see all these things, those are also under biodegradable condition. Okay, now what are the main points of this? These are the non biodegradable synthetic polymers. Then in case of non biodegradable, they are synthetic polymers, they causes pollution, means what? They pose pollution hazard. Okay, if and due to this scientists developed synthetic biodegradable polymers. Okay, as this causes pollution hazard is going to increase this to non biodegradable synthetic polymers, so scientists develop synthetic biodegradable polymers. Okay, and this is due to that they are attacked by soil microbes. Attacked by soil microbes means nothing but this is a natural waste, we treated it as a natural waste, and this is degraded to humus. This is degraded to humus. From this humus we know the very good example of our organic fertilizer, that is a gandul khat, and here it is formation of humus. Okay, in that also there are the vegetables and so many fibers are there. Even you can put your cotton cloth, you can put your hair, and that is, the hair is also nothing but the polymer, and then it is converted into humus. Humus is also one of the just like a spread, hummus is also one of the eating what you are going to say, something preparation, that is hummus, but this hummus here used in another way. Okay, now synthetic biodegradable polymers developed, they contain functional groups similar, this is C, very important, functional groups similar to those in proteins. Similar to those in proteins means nothing but our biopolymer. Tell me which functional groups are present in proteins? Yes, that is nothing but NH2 and COOH. NH2 and COOH, and for that example is PHBV and nylon 2 and nylon 6. Now we will see what is PHBV and nylon 2 and nylon 6. Okay, see now what is that? This is an aliphatic polyester. See, this is what is this? Ester, polyester with name polybeta hydroxy, polybeta hydroxy butyrate. CO is the nothing but the C double bond O link is there. Then again beta hydroxy valerate. Now what is butyrate? It is ATE, means there is a ester, and this is nothing but derivative of butyric acid. Valerate, this AT is nothing but ester. Please remember, we studied this in 11th standard. ATE is the ester and which is from valeric acid. Okay. Now this PHBV, this P stands for poly, S stands for hydroxy, hydroxy is nothing but our OH group, B stands for butyrate, V stands for valerate. This PHBV is degraded by microbes in environment. So this is our synthetic biodegradable polymer. Synthetic biodegradable polymer. Please remember this example. Now we will see how it is going to form. Beta hydroxybutyric acid. See, 1, 2, 3, 4. 4 means this is the acid is the derivative of butane. Butane, and so this is known as butyric acid. Now what is this beta hydroxy stands for? This is alpha carbon next to functional group, this is alpha carbon. 2 alpha carbon, next carbon is known as beta carbon, and on this beta carbon there is hydroxy group. So this is beta hydroxy butyric acid. And the next one is beta hydroxy valeric acid. 1, 2, 3, 4, 5. 5, we are not in the acid nomenclature system. Pentanic, pentane, then pentanic, pentanoic acid, and this is one more word, that is the valeric acid. Again on this valeric acid, on this beta carbon there is OH, so this is beta hydroxy valeric acid. Now what is going to happen? Removal of a very small molecule H2O, means now these are going to condense to each other. We studied this thing, condensed polymerization. So these are going to condense to each other, and see now this thing, this big polymer is going to form. This big polymer is going to form. See what is going to happen? These are N number of, this is also N number of monomers. Now what is going to happen? See here, from here this H, this H is removed over here. Then CH, CH3, CH2 is there. Here it is C double bond OH, C double bond O, O, and now again this OH, and from this H, see now this OH, H, they are going to form H2O. We eliminated this OH, H from this, and that's why here is the condensation, and now there is a linkage in between these two molecules is the oxygen. Again here CH, CH2, CH3, CH2, C double bond O, again this OH and H removed from this, and they are ready to form a bond with another condensed polymer. Can you see this? And that's why we should write this bond beyond this bracket, and to bottom to this bracket we have to write N. This is very important. You cannot make short this bond up to this only, then this is wrong. It should be beyond the bracket. It should be beyond the bracket, and you have to write N. In the reactant you have to write N to the left hand side, of the molecule. In the product you have to write down N to the right hand side. Here it is the right hand side. Getting this point? Next one is the nylon 2 nylon 6. This is again polyamide, just like a protein, of 2 amino acids. When NH2CO, this is our 1 amino acid. And which amino acids we use? That is the glycine and epsilon amino caproic acid. Epsilon amino caproic acid. Remember the structure. This is glycine, NH2 CH2 COH. This is amino caproic acid. What is that? NH2 and this CH2 must be 5. These are the 5. Okay. And here it is COH. So, are you getting this thing? See, 1, 2, 2 carbons, 5 and this is one more, so 6. Okay. And that's why when they condense to each other like this, by removing again H2O, NH2O, then here it is formation of amide linkage, that is C double bond ONH, just like a protein, and the polymer is formed, is known as nylon to nylon 6. These two, for these two, 5 plus 1 6, so this is 6. So this is nylon to nylon 6 synthetic biodegradable polymer. Now next very important polymers we are going to study in the next lecture, that is we are going to start from the rubber. Okay. So up till now we finished it off up to biodegradable. First of all we see the non-bio, what is meaning of the non-biodegradable, then we see the biodegradable, and in that synthetic biodegradable polymers. Thank you students.